All right, you're recording, Professor.
How about that? Magic.
It's working.
That's great. What do we want to do today? We want to talk about homework number 9, which is what you're doing now. And let me give you the good news right away. I'm going to give you until Tuesday to do that. Isn't that wonderful? Supposed to say yes.
Yes.
Thank you.
It's moderately wonderful.
Let's hear some enthusiasm here. Better to spoil your weekend than mine, right? Then we want to talk about homework number 8. That homework number 8, you've probably forgotten by now, but that's when you found all those typos. And then homework number 10, of course, is you're going to find the typos in much of the rest of the chapter. But that was due, I think, on Thursday of next week. So we'll move that ahead to the following Tuesday also. So homework number 9 is now due on next Tuesday, and homework number 10 the following Tuesday. Is that okay?
Yes.
Good. So we're going to talk about those two things. And then before we go ahead and do 3-dimensional supersonic flow and 3-dimensional subsonic flow, we're going to pause, and I'm going to tell you some bad news. The bad news is how people actually do Flutter calculations in practice. And it will seem very convoluted and unnatural to you, but people have been doing this way literally for at least 50 years, and they're unlikely to change. But I will explain how, even though this seems unnatural and convoluted, there is one great advantage. So you have to wait and hear that part of the story. Okay, let's talk about homework number 9. Homework number 9. You have equation 4.2.27. By the way, I'm assuming that if you have any questions, they either revolve around the homework number 9, 8, or 10. But if you have other questions, we'll get to those in a moment. But equation 4.2.27 was the following. You have the lift given by 2 rho infinity A infinity, the density in the free stream, the speed of sound, the free stream. We're talking about plunging motion, so we have a dH dt, and then it gets multiplied by the chord, or twice the half chord. And then you have this interval term, which of course is the part that makes life more interesting. So we have rho infinity A infinity squared, the interval from 0 to t of dH dt, but it's taken to be a function of tau, which is the dummy time variable, never to be confused with t. And then it's multiplied by k, this wonderful function k of t minus tau d tau. Now, as this stands, this is in dimensional form, which is good, because a nice thing about having a dimensional equation is you can check the dimensions. And if the dimensions are correct, that doesn't mean the equation is correct. But if the dimensions are wrong, you definitely know the equation is wrong. So let's check the dimensions. This is lift. It's really lift per unit span, right? Because we're in 2 dimensions. Rho infinity A infinity times h, that's density times velocity squared. These are 2 different things, but they both have dimensions of velocity. So this has the dimensions of pressure, right? Has dimensions of force per unit area. And then you multiply by a length, that give you force per unit length. So this has the right dimensions to be a lift per unit span in this case. Now, from this equation, from the next term, you can do a couple of things. One is you can infer what the dimensions of k must be. So let's look at that. This is pressure again, right? This is dH dt, but then it gets multiplied by d tau. And tau and t are different, but they also both have dimensions of time. So dimensionally, they cancel. So this has the dimensions of pressure times the length, which gives you the dimensions of force per unit length. So that implies that k must be non-dimensional. And when you compute K, you should be able to verify using that formula in the book that K, in fact, is non-dimensional. That doesn't mean the quantities that appear in K individually may not have dimensions, but at the end of the day, when they're all organized as a total entity, K is non-dimensional. So, okay, that makes sense. You're supposed to say that.
Yeah.
Thank you. I need to rehearse a straight person, straight man. Okay, now we're going to non-dimensionalize this equation. Why? Because one, I like to non-dimensionalize. Two, if you non-dimensionalize it, that means I don't have to put in individual values for all these physical parameters. So we're going to non-dimensionalize the left-hand side and make it a non-dimensional lift, or lift coefficient. And the traditional way to do that is take the lift, divide by 1/2 rho infinity u infinity squared, and then multiply by the chord. Or sometimes it's the half chord, so you have to pay attention to whichever person you're talking to or whatever. And again, since this is lift per unit span, these things I'm divided by have the right units, right? It's pressure times the length, which again is a force per unit length. So CL is in fact non-dimensional. So if I'm going to non-dimensionalize the left-hand side, I have to do the same thing for the right-hand side. So let's do that. So I have lift CL equals. Can you read this okay?
Yeah, it's clear.
Good, thank you. Okay, and now let's do the same thing for these two terms. The first term is relatively easy. I have 2 rho infinity, A infinity, dH dt times 2b, and then that gets divided by 1/2 rho infinity, U infinity squared times 2b. The 2b's cleverly cancel. And that's the first term, right?
Yep.
And then the second term is going to be rho infinity, A infinity squared divided by 1/2 rho infinity, U infinity squared times 2b times the integral from 0 to t of dH dt of tau k of t minus tau d tau. Okay? Now let's simplify both of these. The first term, I get a 4, right? One of these U infinities I'm going to associate with A infinity. The other U infinity I want to use the non-dimensionalized dH dt. So, but U infinity over A infinity is what?
1 over Mach number.
I like that. So this is 4 over the Mach number. dH dt divided by U infinity. That's the first term. This is the famous equation that most aeroelasticians already remember, because this gives us the lift coefficient in terms of a simple formula. And 4 over m is the magic number. It's what piston theory says. Without the integral term, this is piston theory. But then we have this other term, so I have to take all this stuff and add it. Now, here, things are going to be a little different. The rho infinities cancel. I'm going to get a factor of 2. I'm going to get a factor of m squared. Okay. And then let's see what happens in here. I want a dH dt, but I want to normalize it by U infinity, right? So if I divide by U infinity, I have to multiply by U infinity, otherwise I'm not obeying the rules. So K I'm going to leave alone because I claim it's non-dimensional. And over here I have U infinity times d tau. And then there was this factor 2b still there, 2b. But this thing, that's a non-dimensional time, right? Which is what we wanted. So this time has now been non-dimensionalized. This is non-dimensionalized. And the only thing that appears in this equation now is this factor, which is non-dimensional, the HDT over U infinity, the Mach number, which of course is non-dimensional, K, which is non-dimensional, and a non-dimensional time. And if I'm going to integrate with respect to non-dimensional time, then the separable limit would be T U infinity over 2B. Okay, so I've just done some of the homework for you. I did the easy part. Remember, the rule is I do the easy part, you do the hard part. So I did the easy part for you. Okay. One other thing I'm going to say about this, although it's not part of the homework per se, but we'll need it a little bit later on when we do Flutter analysis. If I now assume that H of T is a sinusoidal motion, EI omega T, right? If I'm going to non-dimensionalize time, however I non-dimensionalize time, that implies a certain non-dimensionalization of frequency. It's the famous reduced frequency. So we can write this as H bar EI. We're going to non-dimensionalize time as T U infinity over 2B. But if I multiply by U infinity and divide by 2B, then over here with omega, I have to multiply by, didn't give myself enough room. If I have omega and I have T, if I multiply by U infinity and divide by 2B here, I have to multiply by 2B and divide by U infinity here. And this, of course, is the famous reduced frequency. So for sinusoidal motion, in the aerodynamic theory, the only thing that ever appears if you're non-dimensionalized is M, the Mach number, and K, the reduced frequency. Of course, if you have a wing, the wing shape enters in, right? But from a non-dimensional point of view, it's really only the Mach number and the reduced frequency appear. Why is that important? Because I don't want to compute my aerodynamics every time I change density, every time I change speed of sound, every time I change U infinity. I want to minimize the amount of calculations I have to do for the aerodynamics, because that's the costly part. That's the costly part of any Flutter analysis. And now that I am non-dimensionalized, I see that what I really need is a computer code that for a given wing shape can calculate the aerodynamic forces, the non-dimensional aerodynamic forces like lift coefficient, as a function of only two parameters, the Mach number and reduced frequency. Okay, so that's all I want to say about homework number 9. But now we're open for questions on homework number 9. Any questions on homework number 9? Oh, golly. Are you still there?
Yeah, still here.
Okay. All right. I have heard no questions. Either I've been very clear or you're totally confused. I'm going to be an optimist and assume that I've been very clear. But my email address is still working, so send me an email if you have a question later on. Okay. Now let's talk about homework number 8, which is the fun part. I'm not sure anyone found all the typos, but I think collectively you found them all. And so in the spirit of the season, the coronavirus season, you all received a perfect score, even though you had an imperfect input, an imperfect input. But I wanted to go through some of the typical examples of your homework to point out a couple of things. And Ricky, I'm going to pick on you first. And of course, many people got the same typo, so I won't go through all of them. But several of you noticed that in this equation, which appears on page 163, I left out an integral sign. This is an integral over volume, so it would be a triple integral. Of course, if I were a mathematician, I would say I only need one integral sign, but the dv implies a triple integral. But 2 is either too many or too few. So I should either have 3 or 1, depending on whether I'm an engineer, have to be 3, or a mathematician, and they might say you only need 1. Now, Ricky, you were very, very picky. You noted that on the same page, Roman numeral 4 was not aligned. The Roman numeral 4 equation was not aligned with the others. Well, that's true, but I think that's really picky. But even so.
Sorry, I just really like good alignments.
I know. You're absolutely right. You're absolutely right. And then on page 165, there was, I think, 2 P's, and one of them should have been in a row. That was just a pure typo. This is equation 168, which had a Z rather than a 2. And then you wanted to move this equation to the bottom of the list. Well, I think where you put the equation is in the eye of the beholder, right? But, okay, I'll accept that too. I left out a vertical bar on this equation. On this page, there was one of these vertical bars did not go high enough. And Ricky, you were the only one who found this typo. I think you were the only one who noticed that I misspelled aerodynamic on page 187. And then on page 187, actually this P should be a rho, right? I mean, this is piston theory for a gust. This should be rho infinity, A infinity times WG. And then who else can I pick on? Oh, da-da-da. I'll pick on you for a moment. Let's see. Now, you were one of the ones who noted that this equation, strictly speaking, isn't true. There's an extra term involving the curl of the fluid velocity. But of course, later on, we consider potential flow, which means that the curl of the fluid velocity is 0. But strictly speaking, at this point, I hadn't made that assumption yet. So unfortunately, you're absolutely right. And I should rewrite that in the next edition. And then there was just a pure typo here. This should have been the normal vector to that area. And these are the ones that Ricky had also found. Now this one, I will plead that I did not make a mistake here. You wanted to include an extra term, u infinity squared over 2. In fact, several people said this. But recall that this whole bracketed quantity is differentiated with respect to time. So since this is a constant, once I differentiate with respect to time, that term goes away. Would you agree with that?
Yeah, now that I see it, I will agree with that.
Yeah.
I got a little bit confused.
Yeah. And so again, you're not the only one who did that, by the way. But again, in this next term, this is for the perturbation of the speed of sound, which you don't need in the classical linear theory, but you do need, as it turns out, in the transonic theory. Again, for the same reason, this term is not there if you follow through from the previous equation. Then I think I missed a bar here. Again, this is piston theory, and these P's should be rho infinities. And then I think I dropped the u infinity subscript on a couple of terms on page 188. So that was nice. Let's see. Jan Dries, you didn't really have anything new to add, so I'm not going to look at your homework. Bass, I want to pronounce your name again. Groot Nibbelink. How's that?
Yeah, that's pretty good.
It was not bad for an English speaker, right? Now, does that mean something like great warrior, or what does that mean in Dutch? or not?
Yeah,
What
great warrior. Exactly.
Is that what they really? What? Well, I thought Nibelink was some sort of a figure in the forest who did clever things. That does Groot actually mean great?
Yeah, Groot actually means like big or great. Nibelink doesn't really have a meaning in Dutch, I think.
Oh, okay. All right. Okay. Well, you didn't have anything new to add either, so I don't think. So I won't look at yours. You on? Oh, you were the one who again, with respect to this del cross Q term, pointed out that I was being illogical by dropping that term before I made my assumption about irrotationality. And Neil, I think you also had some of the same typos you had found. James Matthew Hardy, otherwise known as Matt. Is that right? You go by Matt. Is that true?
You have the luxury of calling me whatever you want, but Matthew appears.
Well, what does your mother call you?
Is she mad?
Assuming you've been well behaved, what does she call you?
Matthew.
Oh, Matthew. Okay. All right. Either way. Let's see. Did you have anything new to add? No, I don't. Not really. Oh well, and maybe in your next page, you were making a point that in this formula, if you can see that, this is gradient of this integral, and this P1 of rho 1 is meant to highlight the fact that the pressure is a function only of the density. And I think you were willing to give me a pass on that.
Yeah.
Then you were the only one who raised this issue. And I thought I'd made a point of talking about this in class, but maybe not. In the boundary condition, this is on page 174. In the boundary condition, there's some terms like df dt plus u infinity plus u df dx plus v times df dy. And that equals, F is the thing that describes the position of the airfoil or wing. That's equal to the fluid velocity on the body. Now, I think you can really see that this perturbation U is small compared to that, and therefore normally we can throw that away. But normally we throw this term away too, because we assume that V times df dy, well, basically we're assuming that df dx and df dy are the same size, and therefore V again is small compared to U infinity. Okay, that's how we simplify that one away. By the way, as this stands, this is a linear boundary condition in the following sense. F and derivatives of F only appear in a linear fashion, right? So if I truly know where the wing is, then this is a linear relationship. However, in aeroelasticity, we normally don't know where the wing is until we do the calculation. We don't know the motion until we do the Flutter analysis or Gus response analysis. And that comes out of combining the aerodynamic theory with the structural theory. So these, strictly speaking, this term, the small u times df dx, and this small v times df dy would really be a nonlinear term if I were thinking of it as an aeroelastic system. And I don't want a nonlinear theory if I can avoid it. Now I say that, but you should know that almost all the research I do is on nonlinear theories. But if I'm a practicing aeroelastician at Boeing or Airbus, I really don't want a nonlinear model if I don't really need one. So it's very important, excuse me, very important to collect these terms if I want a linear model. In fact, I have to.
Okay. Okay. Thank you for the clarification.
Okay. You're welcome. And let's see. Yeah, Daniela, I think I covered all the points that were covered in your response. And 7 on. I mentioned that Ricky was being very picky, but I can be very picky too. You were concerned about equation 4.1.23. Let's see if I can. That worked, didn't it? Q bar is a vector. That's the velocity vector, right? With the components u, v, and w. So I put an arrow above it to indicate it's a vector. And that's equal to the vector associated with the free stream, which is u infinity times I bar. But then there's a perturbation, but that perturbation is still a vector. And so I still need that arrow. And I think you were saying that I didn't need the arrow, but strictly speaking, I do. Okay, I think that's all I wanted to say about homework number 8 and comments on your fine submissions. Any questions about homework number 8? Golly, this is a very, very quiet class.
I have a question about homework 10.
Oh, okay. All right, yes.
Is there a number of technical errors that we should be shooting for? You said half a dozen for 8.
Yeah, I think it's going to be roughly the same number as I recall. I haven't counted them. I have identified some myself.
Okay.
I think there were actually 1 or 2 you identified in homework number 8 that I hadn't found, which is one reason I assigned the homework, right? Yeah, but I think they're roughly the same number.
Okay, thank you.
There won't be a lot more, but there won't be a lot fewer either. So that's the ballpark. Other questions?
I have a question
No.
on homework 8.
Number 8, okay.
Equation 4.1.21.
4.1.21. What page is that on?
I think it's on 169.
Okay, I'm looking through my. I can dig out the text, but I'm trying to see if one of you had something on 169. I don't see it. Let me dig out the text. What page number is that? Do you have a page number?
Page number is 169.
Okay. Okay.
Yeah.
You want? Can you see that?
Yes. Yes. Yeah. I want to know how the simplification of the dou by dou t term, where it's del phi into del phi by 2, which simplifies to del phi into del phi. Where does the term by 2 disappear?
Okay. Let me. You're talking about this term? Is that the one you're concerned about?
Yeah, the dou by dou t into del phi by 2.
Okay. Well, if I dot del phi into del phi, I get a scalar, right?
Yeah.
And then I take a gradient of a scalar, which gives me back a vector. And then I take del phi into that into that vector, which gives me back a scalar again. So in some intermediate steps, I may have a vector, but ultimately it's going to be a scalar quantity, right? Is that the question?
Yeah, but I want to know how the term 1 by 2 is not included in the next term.
Oh, you want to go from this line down to this line?
Yeah.
Okay. Let me look at that. I'm cheating by looking offline since I have my book in front of me. Well, that term, this term is still here, right? Hello?
Yeah.
So I haven't thrown it away yet.
Sorry, I can't hear you, Professor.
I thought you were concerned that this term did not appear in this term. Did not appear. This term in this equation did not appear in this equation. Was that your question?
I can't see what you're pointing at actually. I can only see the
Oh,
text in front of me.
See, I'm sorry. I have an arrow on my computer, and I thought you could see the arrow. You cannot see the arrow.
I can see the text. I can see the textbook, the physical textbook, the hard copy.
Okay, wait a minute. I can do something else. There, I can do something. You can see my pencil, right?
Yes, yes, I can.
Okay. I thought you were concerned about the fact that this
Not
term,
that, no, not that term. The term dou by dou t into
This
towards your left. Yes, yes.
Okay, let's look at that term. Why does that term not appear?
That term appears, but the by 2 term is missing in the second line.
Well, I think if you manipulate things, this term and this term are basically the same thing, and that's how I get rid of the factor of 2.
Okay.
See, if I take a time derivative of this and use the product rule, I'll get this, right?
Okay. Okay.
Yeah, and so these two terms added together give me this term. I mean, I could have written it in this form too, but I didn't.
Okay. Okay.
So I don't think I've dropped anything. Everything that was in this equation is still here.
Okay.
But except I can combine these two terms by making a certain identification of the fact that these are basically the same thing written in 2 different forms.
Okay. Cool. Thank
Okay.
you. Yeah.
You're welcome. Good question. Thank you. Any other questions? Okay. Well, let's talk about real Flutter analysis. And to motivate it, I'm going to look at a simple 1 degree of freedom system and use that expression for lift or lift coefficient that we discussed right at the start of the class today, okay? Now, I could write down a more general form of the equations of motion for any arbitrary number of structural modes. In fact, that's what you have to do when you're working for Boeing or whomever. But I think it'll be easier to explain the idea if I look at 1 degree of freedom first, and then we'll generalize it to whatever number of degrees of freedom you like.
Professor, I think you didn't share your screen because we can only see your desk right now.
And say again.
I think we can only see your desk right now. Is that same for everyone? You didn't share your screen, right? Your screen of the computer. I mean.
Well, you can still see my. You can still now. You see a blank sheet of paper.
Yes,
sheet of
yes.
paper. Is that right?
Yes,
Yeah.
we can see that.
Okay. I haven't written down anything yet.
Okay.
Oh, those are my notes from Michael to tell me how to turn the machine on.
Yeah, I
and
know
off.
that. Yes.
Yeah. But now I am going to show you some equations. And so what we're going to look at is the following. So this is what I'll call real Flutter analysis. We've done some Flutter analysis up to this point, but the Flutter analysis we've done up to this point has used such simplified aerodynamics that we don't really need to think about what I'm about to discuss. But when we use the more elaborate aerodynamics, even potential flow theory, let alone the Euler equations or the Navier-Stokes equations, we need to do something much more than what we've done up to this point. Okay, so but to start off, let's consider the following. I'm going to think of a mass. That's the mass of an airfoil. I'm going to think of an airfoil which is just plunging, translating. So it's mass times h dot squared, h double dot. That's mass times acceleration. Oops, sorry. Mass times acceleration. Plus, let's say a spring constant, kh times h. I'm going to replace this in just a moment. Equals minus the lift, right? That's our sign convention. But I prefer to introduce a natural frequency, which is k over m, natural frequency squared. So I'm going to rewrite this as m h dot plus omega h squared h equals minus L. And L is 1/2. We'll think in terms of 2 dimensions, but the same thing would carry over in 3 dimensions. Rho infinity squared times 2b times C sub L. And C sub L is proportional to h dot over u infinity. Okay. And it depends on some function of reduced frequency and Mach number. I mean, I could write out that full expression. We had it a moment ago if you want me to. In fact, maybe I should do that. Let me do that again. C sub L is equal to 4 over the Mach number dH dt divided by u infinity. That's the Piston Theorem result. Plus 2 over the Mach number squared. The integral from 0, and we wrote this in non-dimensional form, so this is T u infinity over 2b dH dt divided by u infinity, which depends only on a non-dimensional time tau, excuse me, u infinity over 2b. I'm just saying that this thing depends on time, but now it's a non-dimensional time, times k of t minus tau. They also have this factor u infinity over 2b, but I won't write that down unless you insist. D
Excuse
tau,
me, Professor, I think you're off the screen.
oh, sorry about that.
Thank you very
Sorry
much.
about that. Thank you for yelling at me. Let's see. I'm gonna. Trying to find an optimum thing there over 2b. Okay, this is what we had before for CL, right? And now the point I'm making is this CL is proportional to dH dt over u infinity. That's the key. It's linear in this, right? We have a linear model. But then again, if this integral, if we assume this is an integral with respect to time, right? So if we assume that h is some h bar e I omega t, then I can put that in this integral. And now CL will also be some CL bar e I omega t. And this CL bar, you could work this out as a homework problem. Oops, sorry about that. This CL bar is only going to be dependent on K, the reduced frequency in the Mach number. That's the point I want to make to you, okay? So this CL is CL bar, which only depends on these 2 parameters, times E I omega t.
Just confirming that K is reduced frequency, not stiffness.
Oh, absolutely. This small k, yeah.
Okay.
Absolutely. Stiffness is usually a large k. Yeah. This k, small k, is omega 2b over u infinity. It's the reduced frequency. So the point is, the non-dimensional, for a sinusoidal motion, the non-dimensional aerodynamic forces will only depend on k and m, which is the point I was making a moment ago, right? And that's absolutely key to the strategy that's been adopted to how one does Flutter analysis, because I'm not going to find the aerodynamic forces for any omega, which corresponds to the Flutter frequency. Okay, I'm only going to run my aerodynamic code for different values of Mach number and different values of reduced frequency. Typically, reduced frequencies might be, oh, I don't know, 10. if it's an early stage of design, the rough answer is okay. You might only run it for a handful of reduced frequencies, using the method which I'm about to describe. The idea is you want to be quick. Why do you want to be quick? I once heard a briefing from the head of the Flutter group for Lockheed Martin. They were doing the Flutter analysis for the F-35. He said, we run 7,000 Flutter analysis a day. And someone was asking him, why don't you run a CFD code, which will give you obviously a much better answer. And he said, I run 7,000 Flutter analysis a day. I don't have time to run a CFD code. Okay. That doesn't mean we're not interested in CFD codes. And if we had actually built the airplane and we got into trouble, long after the design is fixed, we might run a CFD code then to try to understand what the trouble is. But when I'm in a design mode and I'm trying to decide what the stiffness and the mass and all the rest of it should be, and I'm running thousands of Flutter analysis a day, I need something that's really quick. Okay. Are you still with me? What says that? Yes.
Yes, we are.
Yeah.
Oh, that's a good thing. All right. Now, I'm going to scan all these notes, by the way, so you'll get them. Let's see. I want to go back up here. Yeah. So let me just review the bidding. Here's our equation, structural equation of motion, 1 degree of freedom. This is the definition of the natural frequency. So here's just the same equation rewritten. I'll call it equation 1 again. This is the expression, the general expression for lift in terms of lift coefficient. But we've just discovered by this excursion that for simple sinusoidal motion, CL, this non-dimensional lift coefficient, can be written in terms of a magnitude EI omega t, but this magnitude only depends on reduced frequency and Mach number and nothing else. Okay, that's the key. Okay, so now we're going to take equation 2 and put it into equation 1 and see what we get. Okay. Here we go. We're going to get M H double dot. See, today is what, April 2nd, is that right? Is that true? We're beyond April Fool's Day, right?
Yep, April 2nd.
That's good, because otherwise you might try to play a trick on me. Okay, plus omega h squared, h equals minus the lift, which is minus 1/2 rho infinity u infinity squared times 2b times CL, which is, notice I'm spending a lot of time on the aerodynamics. Why? Because that's what's creating all the problem with that, both physically and mathematically. We're not going to have a flutter if we don't have the aerodynamics, and we're probably going to spend at least 90% of our time computing CL. 1/2 rho infinity, even with the simplest theory that's usable, u infinity squared 2b CL bar EI omega t. Okay, but I can also write this in the following way. CL bar is linear in H dot over U, right? So I'm going to write this now as CL double bar, which is everything that's in CL with the H dot over U extracted. And H dot over U is I omega H bar over U infinity. EI omega t. Okay? I'm writing this down in detail because I want you to see how it comes out when we start playing our games. Now, we're assuming at this point, we're assuming that H is H bar EI omega t. Why are we doing that? Well, because almost all the computer codes that are written to determine the aerodynamic forces for Flutter analysis make the assumption that we're dealing with sinusoidal motion. In turbine machinery world, I know a lot of you are interested in turbine machinery. In the turbine machinery world, that's even true usually when you run a CFD calculation using Euler or Navier-Stokes model. That's certainly true when you use a potential flow model. And of course, if the model is linear, this is the most general form, right? If it's nonlinear, then life is a little more challenging. Okay, so now I'm going to call this equation 3. Now I've spent all this time playing with the right-hand side. Now I'm going to play a little bit with the left-hand side. So now we're going to have M H double dot is going to be minus omega squared H bar E I omega T plus omega H squared H bar E I omega T. And now we'll just write the last line for the right-hand side, minus 1/2 rho infinity U infinity squared. This should be 2B. I left out the B, sorry about that. 2B CL double bar. And the important thing about that is it just depends on K and M. And then we have I omega H bar over U infinity E I omega T. Now, of course, we're going to cancel out all the E I omega T's. Still with me?
Yep.
Yep.
Okay. Now, this is a homogeneous equation, right? So we're going to take everything on one side or the other. It doesn't matter. So let's take it on the left-hand side. And note that I've got 2B times omega over U infinity, and that's equal to
Reduced frequency.
Reduced frequency. Thank you. So I have Mach number minus omega squared H bar. Well, I can cancel it. I can save myself a step. I want to find a non-trivial solution, right? One solution to this equation is all the H bars are 0, but I want to find if there's a non-trivial solution, so I can cancel out all the H bars. And now I have minus omega squared plus omega H squared. And there's the plus sign now, plus 1/2 rho infinity U infinity squared. That 2B I omega, that's an IK times CL double bar, which only depends on K and M, equals 0, right? Now, this is going to be the equation we're going to solve by some manner or other. So let me tell you what we would like to do in a perfect world. And then I'll tell you what we do in the real world. In the perfect world, which I don't live in, you don't either. In the perfect world, we would want to find the values of omega which satisfies this equation. And in general, omega would have a real part and imaginary part. And because we've assumed EI omega T, it would be the imaginary part which would determine whether or not solutions grow or decay, right? You agree with that?
Yes, we do.
Why not? Why not? Well, what's the problem? The problem is when you try to compute this function of K and M, even for 2D supersonic flow, you have to do it numerically. Okay. And so what you'd have to do is you'd have to assume various complex values of omega, compute this, put it in this equation and see if it's satisfied. And you would have to make sure that in this equation now, which is a complex equation with both a real and an imaginary part, that you have cleverly selected an omega, which makes the real and imaginary part both 0 for the same value of Mach, same value of mass, same value of Mach number. Sorry about that. this is mass, right? This is Mach number. Same value of density, same value of U infinity, all the rest of it. You can do that, and we've actually done it and written a couple of papers on that. But it's really expensive and time consuming because you're trying to find the roots, basically the roots of a complex transcendental equation. And unfortunately, MATLAB doesn't do that for you. There's not a piece of software that does that, okay? If you can create a piece of software like that, that does that computation very efficiently, you will become a hero. You can start a business and sell that to all the aerospace companies. But other people have thought about it and they haven't been successful as yet, but you might want to think about that. So now, in the real world, what do people do? Well, in the real world, here's what people do. And by the way, this was probably only determined after at least a few days, if not a few years of work. What we're going to do is you remember we say we love to make things non-dimensional. We are going to divide this equation by 1/2 rho infinity U infinity squared. And you might say, well, why in the world are we going to do that? Well, trust me, it's a good thing to do. So I've got something that's mass here. I'll write this now as mass. And I'm going to divide that by rho infinity U infinity squared, except I'm going to associate the U infinity squared with the omega. So I'm going to write this as minus omega over U infinity squared plus omega H over U infinity squared. And I'm going to put a 2 up here because I have to take care of that too. And then I have plus IK times CL bar of K and M must be 0. But what I'm going to do is I'm going to specify K and then find something interesting. So I want to construct this as a K. So if I could construct this as a K, I need to multiply by 2B here and 2B there. And then I need to do a 2B squared down here, right? Still with me?
Yep.
Okay, good. This thing is non-dimensionalized. I'm going to call it mu. It's a mass ratio. It's a ratio of the mass of the structure to some sort of equivalent mass of the fluid. Okay, famous parameter in Flutter analysis. This is now the reduced frequency squared, right? This is something I don't know yet. Well, actually, it's something I'm going to compute. So what am I going to do? I'm going to specify the Mach number, specify mu, the mass ratio, and specify K. And I'm going to compute this thing. I'm going to compute the value of omega H 2B over U infinity squared. That hopefully makes this equation 0. And that's easy enough to do algebraically, right? I mean, if I specify all this other stuff, it's easy to solve for that parameter. That's why I'm going to do this, because it's easy to compute this value of this parameter. But there's a problem. I mentioned that this is a complex equation with a real imaginary part. This parameter has to be physically a real number. It's the natural frequency multiplied by the chord divided by U infinity. All those are real numbers. So this has to physically be a real number. But when I do this calculation and compute this thing from this equation, I'll come up with a complex number for this. Now I can compete, I can continue to select the different values of K and M and mass ratio, hoping that someday I will eventually find a situation where this is only a real number. But that turns out not to be very computationally efficient either. So here's what we do. We introduce damping into the system, structural damping, which we haven't done so far. And the damping model that historically was used and is still used to this very day. This was just Theodorson. You want to blame somebody. Theodorson is the guy to blame. What Theodorson says, let's multiply the stiffness term, that's this term, by a factor which is 1 plus IG. I is the square root of -1. And I'll interpret that phase shift associated with G. I'll interpret G as a damping ratio, a structural damping ratio. It also is non-dimensional, okay? So, let me write that equation one more time. What we have now is we have mu minus k squared plus omega h 2b over u infinity squared, but now multiplied by 1 plus ig plus ik cl bar, which only depends on k and Mach number. Okay, so what I'm going to do is I'm going to pick mass ratio typically and the Mach number, and then select several values of the reduced frequency. And for each of those values, compute omega h 2b over u infinity squared times 1 plus ig. And in fact, usually you just define that as, say, some parameter lambda. Oops, not lambda r yet, lambda. It's a complex number, that's the point. And there's no, from a mathematical point of view, I'm just computing lambda. I'm computing this combination. And how do I interpret the values of lambda? Well, the real part of lambda is equal to omega h 2b over u infinity. And G, as I think you really see, is the imaginary part of lambda divided by the real part. Okay? So now, what am I going to do with this? Well, you can do the following. If I've selected K, okay, and therefore I have K is a fixed number, and I've selected U infinity. Therefore, what I want to do is the following. From this equation, I can now determine a possible value of omega, okay, and also U infinity. So I know if say omega h is known, if I know the natural frequency, then from let's call this equation 5, I'll call this equation 6, this equation 7. Then from 6, I know U infinity. Okay. Okay. And then from the and then, by the way, I know from I should, so you know that from the definition of K, I know omega, right? So from here, from my physical system, I presumably know the core of my airfoil. I know the natural frequency. And by computing the real part of lambda, I know a velocity. And once I know a velocity, going back, and I've already selected a K, I know the frequency, right? Okay. And then finally, from 7, I know G. So at the end of this calculation, I know a velocity, I know a G, and I know the frequency. So what can you do with velocity, frequency, and G known? We can plot the following. We can plot frequency versus U infinity, and we can plot G versus U infinity. Okay. And there's only one equation, so we'll only have one root. But if we had a 10 degree of freedom system, we would have 10 equations in 10 roots, and so forth. From this equation, typically for a 1 degree freedom system, typically what would happen is the frequency wouldn't vary very much with U infinity. It might vary a little, but not much. But G typically would start off negative. Is that a good thing or a bad thing? What value of G corresponds to a stable or unstable solution? If I tell you that positive values of G correspond to positive structural damping, is a negative value of G a good thing or a bad thing? You got 50% chance of being right, right? Of course, once you give me your answer, I'm going to ask you to explain it. Actually, you want the G value to be negative. Why?
Is that because at low flow we'll have low excitation, so the system will be pretty stable?
Well, that's true. That is true. But at any value of G, at any value of velocity, would a negative value G correspond to a stable or an unstable system? And why? Well, here's what we've done. We put positive structural damping in the system. On the other hand, we've assumed that the system is neutrally stable. Why? Because we assume EI omega T, and we assume that omega is your purely real number. That form of the solution assumes that we are neutrally stable with neither a growing nor a decaying solution. A negative value of G says to create a neutrally stable system, we would have to add in negative damping, negative structural damping, which implies that the aerodynamic damping must have been destabilizing, because otherwise we wouldn't need to add in negative structural damping. Excuse me, let me back up, I said that wrong. We've assumed EI omega T. We've assumed that the motion is neutrally stable. There is some phase shift due to the aerodynamics. There's implicitly, it's not very explicit in this formulation, but implicitly there's an aerodynamic damping as well as a structural damping. A negative structural damping to create neutrally stable motion implies that the aerodynamic damping itself is positive. And therefore, if the actual structural damping were 0, this would be a stable system. Okay, that's how you reason it. Now, it turns out that sometimes this negative value of G for small U infinity turns around and goes positive for large values of U infinity. This implies that even though I have positive structural damping, I have a neutrally stable solution at these larger values of U infinity, which implies that the aerodynamic damping itself must be negative. And therefore, if my actual structural damping is, say, 0 or near 0, then this would be the flutter point. Okay. Okay. For a single degree of freedom system, what I've just described is how a real industry person, and often a government official as well, and even occasionally an academic, would do a flutter analysis using the more elaborate aerodynamic theories, such as the one that we've discussed for 2D supersonic flow. Okay. And
Professor?
yes, go ahead.
Can you please explain the stability again? The part of positive aerodamping with the negative structural damping?
Yeah, it's counterintuitive, I think. And the first time I heard it years ago, I thought, my God, first of all, I thought, this is what a kludge this is, right? What a terrible idea this is. And then you begin to understand how people have been led to this because of the nature of the aerodynamic model. But here's what happens. We're putting in a certain G value into our model. That G value, if it's positive, represents positive structural damping. Okay. Yet we're assuming that the motion is neutrally stable because we want omega to be a real number so that the reduced frequency K is a real number, which makes the aerodynamic calculation much easier. So we're assuming neutrally stable motion to begin with. And then we're finding the velocity at which the system is in fact neutrally stable. And I think you'll agree that when G is 0, when G turns out to be 0, and we now are assuming no structural damping, that represents a neutrally stable solution, which we assumed in the beginning. So strictly speaking, all this calculation I've just described, it's only really physically realistic or consistent at this point where G crosses the axis and goes from negative to positive. But then the question is, well, which side, the positive and negative side, which side corresponds to stable motion and which side corresponds to unstable motion? So the reasoning again is as follows. If I had, in order to create a neutrally stable solution, which would correspond to essentially a flutter boundary, if I had to add negative structural damping to create a neutrally stable solution, well, I know that the structural damping is always positive, and therefore that can happen, and therefore this doesn't represent a physically realistic, neutrally stable solution. Okay. On the other hand, if I had to add positive structural damping, a certain amount of positive structural damping to create a neutrally stable solution, let's say this amount, this level, then presumably if I have less than that amount of positive structural damping, I have an unstable system. And so in the regulations that, at least in the United States, well, worldwide actually, the regulations that the government entities have for regulating Flutter, they will allow you to assume that G can be as large as 0.02. And therefore, if this level is 0.02, they would say that's the flutter point, and the corresponding velocity is the flutter velocity. Did that help?
Yeah. Thank you.
You have to think about it. I mean, once you start doing these calculations, after a while you think, oh yeah, and you sort of forget about how unnatural this is. But every time I teach this course and have to explain this, I think, oh my God, it must sound like a terrible idea to the person hearing it for the first time. Now, this is not the only way Flutter calculations are done, but I would say it's probably the way 90% of the calculations is done. So let me, I'll tell you the next way the next time we get together. But this procedure is usually called the VG analysis. The G is obvious, right? The V is, I think, shorthand for velocity, right? Because what we're really doing is we're finding G, the velocity, and also the frequency. But it's the VG curve, that the velocity, G versus velocity curve, which actually determines the flutter point, right? And then once you have the flutter point, you go to this curve, and that gives you the frequency at flutter. Okay, I think we have hit the magic hour. Other questions before we conclude for the day? Well, now you've been exposed to the innermost secrets of Flutter engineering and the unusual things that one does, and actually to get a Flutter point. So we'll talk about at least one other method at the start of next class. In the meantime, work hard on homework number 9. And if you're already done with that, you can go ahead and do homework number 10. We'll see you on Tuesday. Be safe.
Sounds good. Thank you, Professor.
Thank you.
Thank you, Professor.
Have a good rest of the day.
Thank you, Professor.
Hi, Professor. This is Michael.
Hey, Michael.
I'm sorry I slipped in a little late today. I lost track of time.
I'm sorry.
I'm sorry I slipped in a little late today.
Oh, no, not a problem. I think I actually hit the right button for recording. One of the other
Yeah, it
students.
looks like you've been recording. You should be able to hit stop now.
Yeah, whatever. I'll scan these notes for you. There are only 4 pages. Hopefully, I won't break the machine when I do that.
Okay, fine.
And if you would distribute them, that would be great.
Of course. If you want to hit stop on record.
Okay, I'm not sure I know how to do that.
Just on the bottom of the screen, there's going to be a stop recording button. It's like a square.
I see stop video. Is that close enough?
Not quite. It's going to be middle of the screen on the bottom near the share screen button, near the chat button. There should be 2 lines and then a square.
I see pause recording.
Yep, right next to that, it should say stop recording.
You know, I think I just saw it. Yes. Yeah, I think I see it.
Yeah, you go ahead and hit that.
See if it works.
Looks like we're still recording.
Oh, really? Okay, let me try again. Oh, I see. Let me try this.